Okay, so first thing I would like to discuss is the solution for the beat generation assignment. So the output you want is that you have right in an infinite loop. Now this is called this is, let's say, y of n. Can I see y of n using DSP? That there is a filter which is operating on some x of n. What can be my x of n? Problem is I want to generate an infinite metronome. For example, I have given you audio sounds, let's say clap, single sound I have given, and I want you to run it in a loop at a given BPM. I can change the BPM using a slider and then BPM will change. Or I may give you two different sounds like this one and this one. And I will say, play me a metronome which does 1, 2, 3, 4. 1, 2, 3, 4. Like that. So something. So that's the problem. And you did it in the assignment. So the one way which you can use is, let's take a filter. The input to the filter is x of n, and x of n is simply periodic impulses. Let's say this onset happens at 0, this onset happens at t, this onset happens at 2t, right? And this is also 0, t, 2t, right? So my x contains periodic impulses which are at a time period of capital T. There is a time period I want in the output. And my h is one particular sound. Let's say it's a clap sound. Which means whenever the input is basically h of n is the clap sound starting at 0. Onset is at 0. This is my h of n. Right? Now what will be my output then? Clap, 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 clap. Right? Now let's say if you want to make clap, clap, thuk, clap, clap, thuk. What will you do? Huh?
You just like pass these filters series and for each filter. I mean, for xn we can pass 2 times that the h and then some other waveform. So.
But how will you change h? You will say my h is now a tick instead of a clap. Clap, clap, tick, clap, clap, tick, clap, clap, tick.
Maybe some form of time delay multiplexing.
What is that?
So basically, based on the time of the base signal, what part we want to play can be selected.
Sent into?
Can be selected. What part can we want to play at a particular point can be selected. So if it is 2 times h and 1 times h dash, then we can say 0, 1 we can set a 3 repeat like 0, 1, 2 loop. Then every 0, 1 we play h and then h dash. Then
How do you go to h dash? What is h dash? Yes.
We can pass xn to 2 parallel systems.
Yes.
One will generate beats for h and other will generate beats for h dash, and we can simply add both.
Yes. Very good. Very good. Let's say this is my xn. 0 and t I pass through here, and 2t I don't have anything here. Then again here 3t I again have this, 4t again I have this, and 5t again is empty. This one I pass through my clap, and the other thing where I have here is I pass through the tick sound. Right? So what I will get in the output, I will just add them up. I get here clap, clap, tick, clap, clap, tick, clap, clap, tick, that kind of sound. Right? simple, very simple DSP, right? So if you could do this, then you get good marks. But I'm sure you must have suggested some other methods which are also very competent, right? Okay, now the thing here is, if you want to adjust the BPM, what will you do? To adjust the tempo, what will you do?
So this is for the BJJ assignment, right? So in that case, you take a constant clap and just repeat it, right?
Uh-huh.
You don't change it like this.
Yeah, that's fine. I'm just telling the concept. You can modify it as per the assignment exact statement, problem statement. To change the BPM, what will you do? Change capital T. Change the spacing between two consecutive beats. That's it. Now, this can do. This is a kind of offline system, right? You make an array and then pass it through a filter, add them. It's an offline processing. Can you do it in real time? Can you do it in online fashion?
Yes, sir.
How?
So I had submitted it.
Achha, okay. fine. I just for discussion, for the sake of discussion. And so I will go through those solutions also. But how do you do it? You can discuss your answer.
Okay, so I have first made a larger array for 20 seconds and appended the every time the array changes, either when the playing comes to an end or the slider values change, and every time according to the slider values, the array gets updated and the array is played infinitely.
Okay, good. So basically, you are generating something like a buffer, a circular buffer, where as the entries are dequeued from here, the queue, you are adding some things to the queue. It's like a queue in the signal. Oh, what is it called? Data structures.
Yes.
A queue data structure, right? Yeah, good. We read something called overlap add method. You could have also used that. When do you use overlap add method? When hn is finite and xn is potentially infinite, or means it is very large, and it can also be for real-time processing. So you can use overlap add method for real-time generation. My xn, as you said, if the buffer thing can keep getting generated, and then you use overlap add method to generate yn. Okay, just write it down here.
So for this problem for real-time BPM change, I had come across something called time stretching with constant pitch.
Okay.
And it had some of these methods. I don't remember the name, but sequential overlap add was there, I think.
Mm-hmm. Okay, that's it. This was one. Okay, now let's discuss something. Last time we were discussing about MFCC features, right? Mel frequency capital coefficients. So what is this mathematically? You found your x k comma m, which is simply the STFT, right? You took the magnitude of this, you multiplied it with a Mel filter, or a kind of what notation did we use that time? V. Right? This VL is a Mel filter. It's kind of, I hope you remember it, right? It's a Mel filter bank. So there are L filter banks. Let's say L goes from 1 to capital L. So these are the filter banks. It's a filter bank which has got L filters. This whole thing is a filter bank. It's a bank of multiple filters. L number of filters are there in this. Okay, and so we get S, L, comma, M. How does it look like? I hope you have seen in Pratt or somewhere how does the MEL spectrogram looks like. The MEL spectrogram looks like a normal spectrogram, but then frequency is on the MEL axis. So which means, okay, just a quick question. If I say at let's say 100 hertz, so where will I get the peaks? This is my frequency axis. This is my time axis. Where are the peaks in frequency? I'm saying, let's say my fundamental frequency is 100 hertz. At the 100, 200, 300, 400, right? Like that. I get my peaks, right? Now if I convert it into, this is the simply STFT, mod X. So basically this F is basically indexed with K, T is indexed with M. So, but if I go to MEL spectrogram, this means S, L, comma, M. This is frequency, but then we use L here. This is time, M only. How will the MEL spectrogram look like? Oh, plus there were some changes right here. You have log and all that stuff. Sorry, this is a log is here, plus 1 is also there. Right? Log and then plus 1. I think we discussed that earlier. Let's not. Okay, tell me what is SL, comma M. How will it look like? So my center frequency is kind of log scaled, right? It's kind of scaled on a log axis. So this will be 100. So, okay. So my frequency, this is my MEL frequency. What was the formula? Do you remember? It is something, just a minute. I will use the notation which I used earlier. Notation is FC on a MEL scale. This is 2595 log to the base 10 1 plus F upon 700. Right? So now tell me where will the peak go? Right, so you can check. Let's see. When my F is 100, where is the peak? Log 1 plus 1 upon 7 into 2595 something. Right, so can you calculate what is that? What is the value? Likewise, when F is 200, where is the value? When F is 300, where is the value? When F is 400, where is the value? You can compute your center frequencies, and they will be not spaced equally. They will be like decaying spacing. Generally, we say it's a MEL scale, but generally we can simply say log of F. So let's say log of F, this is 2, this is 2 plus log 2, this is 2 plus log 3, this is 2 plus log 4. Right? This is the log scale, not MEL scale, but log scale. FC is simply log of F, log to the base 10. Right? So you can see that the distance between adjacent peaks is independent of F naught. It depends only on the number, which number it is. It's second harmonic, third harmonic, fourth harmonic, like that. All right? This is what we discussed. Now, this is called Mel frequency spectrum or Mel spectrum or Mel spectrogram. Now, what is MFCC? What is the dimensionality of capital S? It is, let's say, 40, 50 or something like that, or large, 100 possibly. But you want to compress it even further. And we can compress it by applying a, oh, just a minute. Why do we compress it? I didn't tell the reason. You know the reason. I gave the assignment to you. What is the difference between A and E? What's the difference between A and E and U? This was a question in the quiz also. How many of you could do it? Raise your hand. You could do it?
Explain something in the lecture, like one of the lecture which you have taught. The spectrum was slightly different. The R1 is slightly a random spectrum, and the E was slightly smoother or something. One of the lectures explained.
Okay. So it's like this. When I'm saying A at a frequency of 100 Hertz, one thing is for sure that I will have peaks at 100 Hertz, 200 Hertz, 300 Hertz, etc. The periodic, the integer values. So this is my right in the dB scale or something, 20 log or something, and this is my frequency. This is my frequency in Hertz. Right, 100, 200. So when I see E, it will be like this. Same frequencies will be same. But what has changed? What has changed? This shape has changed. What has changed is the envelope over the peaks. Peaks are at same location, but their heights, their relative heights have changed, which means the envelope around the peak has changed. So there it was like this, here it is like this. Now go back to your old assignment, second assignment I think, and check that this is what you obtain. When you say, let me do that exercise today in the class also, and you can check. Okay, now let me do it because I think it's worth spending some time on that. Because if that is clear, then Prat new sound, record mono sound. E, U. Just I made two recordings just so that something goes wrong. Spectrogram. How much? What should be the window length I should choose? Any suggestions? I use 25 milliseconds. My frequency is about 100 Hertz, let's say, or 150 Hertz. Then the window length will be how much? What is my time period of my 10 milliseconds? For 100 Hertz it is, yes, 10 milliseconds. So for 150 it is less than 10 milliseconds. Huh? Okay, So I have taken my window length to be of 25 milliseconds, which means it will contain about 3 cycles probably. I can take even smaller to include less number of cycles. 20 milliseconds. So what you see here is, this is A, you can hear. E. E, E, U, U. You can see here you have dark bands extended to quite some height. Oh, actually this is only 1000 hertz, so let's also change this viewing range. View range, let's say we go to 8000 hertz. It's still very sharp. I want to make it a bit more I want to reduce the frequency resolution.
20.
I'm using 20 milliseconds.
This is 20,000 hertz.
No, that is. Let's increase this dynamic range and let me make the window size even smaller. 15. Doesn't help. Probably you can see that here I have a lot of energy in these regions, and here I have very less energy in this region, more energy here, right? Pitch is almost same everywhere, so I remove pitch. Pitch is not required. Now you can see formants. Okay, what are formants? Just now we got some peaks in the spectral envelope. The peaks in the spectral envelope are called formants, right? The peaks in the, not in the spectrum, but in the spectral envelope, they are called the formants. Let's say show formants. So you can see in R, the first peak and second peak, they occur quite close to each other. Third peak is a little far. But in E, there is a lot of gap between the first peak and the second peak. And in U, you have some other structure. Let's say the first peak is there, second peak is kind of little far, maybe sometimes here, but then far. And the third peak and fourth peak have larger distance. So this is roughly how these spectrograms look like. And you can see their spectral peaks are very different. Or the peaks in their spectral envelope, they are quite different. Got it? A and E. E has long gap. It's called F1, first formant frequency, second formant frequency. This is first formant frequency, second formant frequency, third formant frequency. Called F1 means the formant frequency. F is called the formant frequency, and 1, 2, 3, 4. So here F1 and F2 are very far apart. Here F1 and F2 are very close. Okay, so this is what we have. This is the DTFT. This is how it looks like. So now the thing is, when to distinguish two vowels, we don't need the information about their fundamental frequency. Huh?
How is this frequency different from the spectral frequency that we are getting the maximum of?
Okay, I'll go back to our right, this is the A sound, E sound, A, E. These are the envelopes and these are the peaks in the envelope. F1 and F2 are quite far. Here, F1 and F2 are quite close. Here, F1 and F2 are quite far. So this is the difference. So now we are not interested in the individual peaks. We are only interested in the envelope about the peaks, right? This is called the. So now to capture this, which means we can construct some features which are very compact and they're also informative. How can we construct such features? By only extracting the envelope information and ignoring the individual peak information, right? Okay, now tell me from your current understanding, how will you extract the peaks, sorry, not the peaks, but the shape of the spectral envelope? How will you extract the shape of the spectral envelope? And how will you ignore while ignoring the peaks? Quick question.
Just take the max value of each peak and just store it.
Okay. So yeah, that's a very good answer, that you take, let's say, the max values of every peaks, all the peaks, and then just save them. They represent, that's a good feature representation, right? Let me write it down. So, features to distinguish yeah, so one suggestion is peak frequencies, huh? Any other feature you want to use? Okay, there is a limitation with this feature. There is one disadvantage of using this feature. Let's say I speak at a frequency of 150 hertz, and then there is somebody who speaks at a very high pitch at a frequency of 300 hertz. So my vector will be of length, let's say 10. That person's vector will be of length only 5. Let's say my DFT has 8000 hertz, means the DFT resolution is up till 8000 hertz. The capital N is, let's say, 8000 or something. Then what will I get? I will get more number of peaks than the other person, right? So this means this feature is a good feature, but its length is not constant. That is a problem, which means I cannot feed it as an input to my neural networks or any other parametric model which has got fixed input size.
We can extract the histogram of the spectrum with constant pin size, with fixed number of pins.
Very good. This is a better suggestion, means this addresses the issue. So we use histogram to extract energy in different bins, right? So actually when you did filter bank, it's exactly the same thing. Histogram has very sharp bins, but filter bank had soft bins which were kind of intruding into each other, right? So this idea is that of filter bank. Yes, it's like a filter bank. Good. So this means you can reduce the size. But what size of filter bank? What size of filter bank should I use? How many filters should it have?
So you could start with first considering 0 to 20,000 hertz as vocal range, so we can have like 20 filters, and based on the accuracy requirement of our features that we can increase the filters. That would be less than 20,000 obviously.
Very good idea. Yes, we can certainly use. Now, notice here, I may like to place my filters on a logarithmic axis or MEL axis rather than placing it on linear axis for the obvious reason, right? Sensitivity has to be uniformly distributed. So yes, so this is called So a feature which is very popular is called log filter bank energies, LFB, which exactly is the same thing. You have a filter bank on the log scale or mel scale. Mel scale is also log scale. So, and energy means the output of that filter, right? That is LFB feature. It's very popular and useful for speech recognition or distinguishing between different phonemes, right? Any other feature? Any other feature you can think of? Maybe I will help here. If you apply a Fourier transform on this, if you apply a Fourier transform on this, what will you get? It has got Fourier transform, low frequency components and high frequency components. What are the high frequency components of the DFT of this mod x or the log of mod x, whatever? The DFT of this, what will be the high frequency components?
Closer to that from DF to
No.
Like,
You are applying a Fourier transform on this signal. This is my x. You have to apply Fourier transform on this, you get capital X. So that Fourier transform, it will have peaks at 100 hertz, right? 100 hertz. Because this signal is periodic, kind of periodic with 100 hertz. That will have peaks at, no, not 100 hertz, depending on the sampling rate, okay. So basically, this signal has got high frequency components which will be covering all the peaks, and low frequency components will cover the spectral envelope. So which means if I apply a DFT on top of it, and if I just take the low frequency components of that DFT, they will capture the spectral envelope, and the high frequency components will capture the individual peaks. Is that point clear? Is that point clear? If we apply DFT on, okay, log also there, on log this thing, high frequency,
I didn't understand that.
its high frequency components will contain peak information or the spectral peak information, and its low frequency components will contain spectral envelope information. And I'm interested in spectral envelope, so I will simply take the low frequency components of that DFT, and I'm very happy with it, right? So therefore, take low frequency components of DFT x k comma m, right? Now there is a problem. When I take DFT, it is a complex number, right? DFT returns a complex number. Now tell me, if my signal looks like this, the DFT will be real or imaginary, or real or complex? DFT will be, the DFT of this signal will be real or complex. Let's make it more general. Let me Okay, just for this is the final conclusion where we are heading to, but why we are heading there. So let's now discuss what is DCT, discrete cosine transform.
Can you explain how you concluded that the high frequency information of the DFT of DFT would have the peak representation and low frequency spectrum?
Okay. Let's say this is my signal. I multiply this with, this is k here, e to the power minus j let's ignore m for the time being, we are considering single window only. M is not required, single spectrum only. Summation over k. Right, this is my Fourier transform. I have to multiply my x with a sinusoidal signal, and this sinusoidal signal has a frequency k upon capital N. No, p by capital P by capital N. K is the running index here. So which means this is my xk. Let me so what is this signal? This is my e to the power minus j 2 pi I will get a peak for this particular p. For this value of p, I will get a peak. So for this p, when p is such that I will get a peak here. And likewise, when my p is like this, which color should I use? Right? I'll get a peak here. P dash. Right? It kind of matches with this this kind of structure, right? I think I made it a little bit shifted. Let me try again. Oh, sorry. I get a peak here also, right? Because this frequency matches the yellow frequency. So this is P dash. So I got kind of high values around two types of coefficients. One are these P, others are the P dash. Which one is larger? P dash is large or P is large? Tell me what is bigger? P is bigger or P dash is bigger? P is larger than P dash. Do you agree with this? So this P dash are the low frequency components, they capture the spectral envelope. And P are the high frequency components, they capture the individual peaks. Clear? Anybody has any questions? Okay.
Can there be low frequencies that don't follow the envelope?
Which don't follow the?
That don't follow the envelope.
Don't follow the angle of?
Envelope.
That don't
Envelope.
follow the envelope.
Yes. So basically, since this signal is not perfectly periodic, right? So we don't get a single peak. We will get kind of a region, means a kind of curve. right? So therefore, all the p's around that p dash will capture the shape of the peaks, or shape of the spectral envelope. So we generally take, let's say, top 20, the values from 0 to 19. So all those values of p, or x of p dash, for all those values of p dash, so between 20 values will represent my spectral envelope. And as I keep going up, as I keep increasing my p, I will start getting information about the finer details of the spectrum, the individual peaks of the spectrum. And if I go very high, then I will get the spectral peaks. Right. Okay, now let's discuss about discrete cosine transform. Now the question is, we have DFT, which is complex. I want another transform which is real, which gives me real outputs. It doesn't give me complex numbers as output, or which means I want a kind of DFT which is always real. So tell me the condition. When do you have a real xk? Let me first write down. Okay. Right? So if I say my xk is real, when will that happen? For any xn is a finite signal of length, let's say length 3, 0, 1, 2. This is my xn. And capital N is simply 3. Right? How should xn look like so that my xk is real? What is the condition? You have seen it in the previous lectures. So basically you will derive it like this. Xk is equal to xk star. Right? This means right? Because if my small x is also real, right? My small x is also real, then this is equal to x of minus n. Right? So, sorry, the negative sign, x of minus n, sorry, x of minus n. Now, when is this true? When xn is equal to x of minus n? Because it's a limited signal, so, or it's a kind of modulus take. So x of n is equal to x of n minus n, which means my x is symmetric. Now, for any general x, this is my x of n, for any general x, we can't ensure that this is symmetric, right? It's not symmetric. But can we create an x or a kind of a new signal using this signal which is symmetric? How?
2n length signal which is a copy.
Very good. Take a signal of length 2n. Oh, sorry. Let's call this as x tilde n. So my x tilde n is of length 2n. 0, 1, 2, 3, 4, 5. So it's of length 6 from 0 to 5. And if you take a DFT of this signal, it will be a periodic, it will be a real DFT, right? it will be a real number, right? Which means it but if you take its DFT, the formula will look like, so how will you take? You say, let's say my x tilde k is equal to summation x tilde n e to the power minus j 2 pi k n upon capital N, sorry, 2n, n goes from 0 to minus 1. Alright? If you convert it into x of n now, this is equal to something like this, right? Right? And then when you simplify it, you will get a bit complicated form. It will be correct, but little bit too many terms, and it may not simplify to a very nice looking expression. So what people do is, now this is an engineering trick which comes by spending some more time. You can derive it on your own, but just to save some time, I will just tell you the trick. The trick is like this. You map it like this. So what is the length of the signal? 4n. And there are blanks in between. There are blanks in between. Right? So finally, the formula which you get will be like this. My x of k, the whatever tilde, is equal to summation x of n This is the formula for discrete cosine transform. Everything is a part of cos. Right? So basically you construct a signal of length 4n and insert zeros in between, and then when you simplify this, for this particular x tilde, this is x tilde n, if you will compute your DFT, it will simplify in this nice looking expression. Right? All right? This is called the discrete cosine transform.
So why do we insert zeros in the middle?
Pardon?
Why we insert zeros there?
Just to make it come in this nice form. If you don't insert zeros, you will get okay, I can give it to you as a reading problem, reading assignment. there are different kinds of DCT. Some DCT, they use this representation. They apply DFT on this and they get a real transformation, they call it DCT. But the formula is not as clean as this. They will have some x0 into something plus x from xn equal to 1 onwards, you get some this kind of expression. For x0 you have some other expression, like let's say xn upon 2 or something like that, which does not look like one term or one single term to be added. You have to add some extra terms also. It doesn't simplify into this nice form. So this is called the DCT of type 2. Like there are 4 types of DCTs. But the other DCTs, they use this kind of things and they don't simplify. They don't look as good as this. So generally people use DCT of type 2, which is this. Just it is easy to memorize, easy to use, easy to implement, etc. Okay, this was all about discrete cosine transform. Now we will see the next topic, which is time series analysis. To teach time series analysis, I would like to motivate you with Z-transforms. We have seen DFT, we have seen DTFT. Now we are going to see Z-transform. And Z-transforms are very good for real-time processing. Right? I'll show you how. Let's start with DTFT. What is DTFT? X e to the power j omega. How many of you know DTFT? Okay, everybody knows DTFT. Is equal to summation of x of n e to the power minus j omega n. So my xn is infinitely long and my Fourier transform is continuous, which means my xn is aperiodic, this is continuous. DFT is when you make this periodic, this becomes discrete. That is DFT. So DFT and DTFT have very close relationship. So this is DTFT. Now, this DTFT will exist. When will it exist? When this series will converge. When will this series converge? This is an infinite series. It will converge when absolute value of xn is less than infinity. When absolute value of xn this is bounded. Right? But many a times our signal may not be bounded. So what we use in that case, DTFT is not defined because it will not converge. Therefore, we define something called a Z-transform. The observation is, what is e to the power j omega? What is e to the power j omega? On the complex plane, say if I have a real part of Z and imaginary part of Z. So what is e to the power j omega? It's a point on the unit circle. 1 minus 1 I minus I, and the point on this is e to the power j omega. Now the question is, why do we only confine ourselves to e to the power j omega? We can go to any point in the complex plane. So let's call that point as Z, and then x of Z is equal to same thing, summation of xn Z to the power minus n. So basically e to the power j omega gets replaced by Z. Now the condition for convergence becomes this. Now, if my x of n is diverging, still I can choose my z large enough so that the whole series may converge. You all know what is the infinite series and how do we take. So which means let's say my z is equal to r times e to the power j omega, then r is the magnitude of z. I can always choose an r so that, or I may be able to choose an r which so that it converges, right? So this is the advantage of Z-transform. This is one advantage, which is very theoretical advantage, but the practical advantage I'll show you in some time. Take an example now. For this signal, compute the Z-transform. For this signal, what is this signal? What is un? Step function. Means for n less than 0 it is 0, for n greater than or equal to 0 it is 1. Can you compute the Z-transform for this? Oh, first compute the DTFT. DTFT is equal to Is that clear? Is that correct? This is an infinite series and it sums to 1 upon 1 minus r, where r is the common ratio, which is a e to the power minus j omega, right? And this series will converge only when my r is less than 1, so which means my mod a is less than 1, right? So this means it may not exist if my a is greater than 1. It won't exist if my a is greater than 1. Let's now take Z-transform. So what is x of z? And this is this series will exist for if I choose my z to be greater than a, means mod z is greater than mod a, then this series will converge, right? So that's the advantage of using Z-transform, that I'm able to represent my signal into a very compact Z-transform looking form, and I can work with it. And this region, let's say my A is somewhere here, the region outside here, so my Z can exist here. This is called the region of convergence. Because if my Z lies in this region, then the series will converge. Therefore, it's called region of convergence. Right? This is simple DFT, simple DSP, which you have already read in your other courses. Right? If you are not able to understand, please ask questions. If you don't ask questions, I'll keep going forward and you may not be able to catch up. Ask questions. This is known to you, right? Okay. Now, our ROC could be either, generally it is of three kinds. Either my ROC could be like this, which means inside a circle, or it could be an annulus, right? Or it could be outside the ring, means whatever, outside the circle. Generally, ROCs are in circular shapes, either a disc or a ring or a punctured disc. Right? Some common forms of Z-transform. What's the Z-transform of Z? Delta n. What's the Z-transform for delta n? Quick, apply the formula and find out. Just apply the formula. 1, simply 1. For delta n minus m. Very good. That's it. This observation that a delta function corresponds to simply a single term of z, right, of some degree. This is a very useful observation, and we will explore it in the next class. It's almost 3:15 now. We will do it in the next class. Yeah. So, any questions? We have our mid-sem exam on Sunday, right? So, any doubts, or do you want to have any extra class or any doubt session for that?